Okay, can you hear me in the back? Great, fantastic. It's a beautiful day today. So let's get this over with so that everyone can go and enjoy some sun. So today we're continuing our discussion of support vector machines from last time. Remember SVMs, a new type of linear classifier that we're studying. A bit more of a geometric perspective than what we've seen before, where what it's trying to do is essentially maximize the margin, maximize the distance from the separating hyperplane to any of the closest points on either side. So what we're going to do today is we're going to derive another version of SVMs that are used when the data are not linearly separable, when there's no actual line that we can put that perfectly separates class 0 from class 1 or class -1 from class 1. And this is what we call the soft margin SVM. So this is quite important because actually in practice, basically nobody uses the SVM that we talked about last time because it's basically never the case that you actually get data in the real world that are perfectly linearly separable. It just doesn't happen, right? You have noise, you have outliers, you have whatever else, but you need to deal with that somehow. And the way that people deal with it, at least historically in the context of SVMs, was using this thing called the soft margin SVM. So this is quite important. And basically what this version of the SVM is going to do is it's going to introduce another hyperparameter, right? So something that we set ourselves, which people usually call C. Sometimes people call it lambda. It doesn't really matter what you call it. But what it does is it trades off between maximizing the margin, right, which is what the goal was last time, versus actually being able to correctly classify all of your training points. So basically, we're going to introduce this bit of a, this fuzzy area where maybe we don't have to be perfect on our training set because we can't be, right, because there's no line anyway that separates all of the points. So if we can't be perfect, we're going to say we're allowed to be wrong in certain cases as long as we're still trying to maximize the margin on the rest of the data points that we are classifying correctly. That's basically the intuition behind the soft margin SVM. So we're going to analyze, we're going to, write out what soft margin SVM actually is, and then we're going to analyze things like what effect does varying this hyperparameter C actually have, and then we'll also see how this constrained optimization problem that we'll come up with in a second can actually be written as an unconstrained problem, which is kind of nice, using something called a Hinge loss, which we'll also talk about. But let's start by actually reviewing what it is that we did last time, right? So remember that our optimization problem from last time for the hard margin SVM looks something like this, right? And we went through a whole lot of math to actually derive this. But in the end, what came out was fairly nice, right? It's just minimized, the 1/2 times the 2 norm squared of my weight vector W, subject to the constraint that all of my data points are classified correctly. And not just correctly, right? They also have to lie at least one away. Essentially, that's the margin that I'm defining, right? So this is what we had last time. And this is known as what's called the hard margin SVM. I don't remember if I actually used this term last time, but this is what people usually call this. And we call it a hard margin because the margin can't be violated, right? It's hard in that sense. And this is what is known as a quadratic program, right? So it's actually, a fairly easy type of optimization problem to solve, and there are really good techniques for doing this. But we said that there actually is only a solution if our data are linearly separable, right? So if there's actually some line, some hyperplane that we can draw that perfectly separates the negative class from the positive class, then we will yield a solution from this optimization problem. And specifically, that solution that we'll get is the max margin linear classifier, right? But the problem is, if our data are not linearly separable, so there are some points that are mixed in, that there's no line that we can draw that is perfect on all of them, then this QP is just going to fail, basically. It won't return you anything. It'll just say that all of these constraints can't be satisfied at the same time, right? So there's nothing that we can do in that case. And this is a really important question when it comes to real-world applications, because like we said, it's basically never the case that you actually get data that are so clean and noiseless that you actually get linear separability, right? It just doesn't really happen in practice. And so it's really important to try to figure out what do we do in the case when the data are not linearly separable. That's going to be the main question for today. And so let's actually draw a little bit of what something like that could look like. So let's say that this is my data set like we've always had, right? And this data are linearly separable, right? we actually have lines that we can draw that perfectly separate, this green class from this red class. And, I can draw data points that, might make my margin smaller. It might make the overall problem seem a little bit less, desirable. Like, for example, if I had like an x over here or something like that, that's going to violate this particular linear classifier, but there are still other linear classifiers that I can draw that, are valid for this case. And so, situations like this, they're not desirable, but we can still handle them using the formulation that we've seen so far. This is still a linearly separable data set, right? But what if I, draw a point out here, right? And what could this be? Well, this could be, something like noise. Maybe the measurement was really inaccurate there. This could be like human error, like maybe that actually is a green circle, but someone accidentally labeled it as a red X or something like that, right? Like that does happen in practice. It could just be some kind of weird outlier. Like, maybe there's some random process that's governing how this data is generated, and maybe the random process, spawned an outlier, and it might not be any kind of error at all. It might just be, undesirable in that way. So if that's going to be the case, well then, we can pretty clearly see, based on this drawing that, there's going to be no separating hyperplane anymore in this case, right? Like there's no blue dotted line that we can draw that's actually going to be perfectly accurate on all of these examples that we've been given. And so in this case, our hard margin SVM is going to be no good anymore. There's going to be nothing that the hard margin SVM can actually do in order to find us a separating hyperplane, a max margin linear classifier that actually works. So that's the issue. Okay, so then intuitively we might start thinking, well, if that's the issue, then maybe what we need to do is we need to introduce some kind of leeway in terms of like, well, maybe we don't need to get all of the data points correct, right? Maybe that's not actually possible. We still want to get as many of them as correct as possible, right? But maybe some of them we kind of just have to give up on and say, well, this is, maybe this is noise, this is outlier, this is error, whatever. I'm just not going to really try that much on this one in order to do better on my other data points. And this is exactly what we're going to do. So we're going to introduce this concept called slack, which is basically the mathematical formulation for how we're going to quantify that intuition that we just built. Okay? Specifically, we're going to do the following. We're going to account for data points that lie on the wrong side of my decision boundary, okay, by having a slack variable, which I call xi, right? So this is that Greek letter. It's pronounced xi. In my opinion, it's the worst Greek letter because it's really hard to write. But that's a story for another time. So it's a slack variable xi that we have for every single data point xi, yi. Okay? So we have xi1 all the way up to xi n, where n is the size of our data set. Right? We're going to have one of these for every data point, and it's going to quantify how much we're willing to sort of give up on that data point. Okay? How much we're willing to let it lie on the wrong side of our decision boundary, or more specifically on the wrong side of our margin. And we'll talk about that in a second. So we're going to change the constraints that we had before to look something more like the following. So before, what did we have? Okay? All we had was this. This was our constraint before, right, for all I, right? So now what we've done is we've said, well, this used to be a hard constraint that every single data point had to lie at least this far away on the correct side of the decision boundary, right? But now we're saying, well, actually, maybe it doesn't have to be perfect, okay? It can be, violating that margin, violating that constraint by some factor of xi I, where xi I is greater than or equal to 0, right? So if xi I is 0, what that means is that data point is fine, right? It's on the right side of the margin, it's correctly classified, everything's good. But if xi I is greater than 0, right, then we're going to let that data point sort of slide into the territory that it's not supposed to be in technically, but we kind of have to let it do that in the case where the data are not perfectly linearly separable, right? So that's the high-level idea. So we're allowing our data points to violate the margin. So let me give you another picture of what that can actually look like. So if let's say this is my data set, and then this is the hard margin SVM returns me this max margin classifier, and then the margin, right, is this sort of like band that we have here that's like running parallel to the decision boundary, and it's the same distance away on both sides, and it's sort of defined by whatever the distance is to the closest points, the support vectors that we had before. This is how we visualize the margin of my classifier. Remember, the hard margin SVM was all about trying to maximize this margin, right? Trying to find the decision boundary that maximizes this. So now, basically, what I'm saying is, in the soft margin SVM case, maybe I'm going to have situations where I don't actually correctly classify every single data point. And if this is the case, then that data point is not satisfying, yi times W transpose Xi plus B is greater than or equal to 1. It's not doing that anymore, right? All of the other data points that I originally had are satisfying that, right? Here, that's not going to be the case. It's going to be, it's going to be satisfying that for some 1 minus xi I, right? For the xi I corresponding to that data point. And specifically, it's going to be, this amount right here. That distance of that vector is going to tell me what that xi I needs to be, right, in order for the soft version of that constraint to still be satisfied, okay? So it's not greater than or equal to 1, but it is greater than or equal to some xi I for that specific data point, that specific I. And similarly for that other data point that I drew that straight up just made the data not linearly separable, right, there's going to be some other xi I here corresponding to this data point, right? That's basically the distance of this vector. And you can see that this xi I is going to be even bigger, right? Because it's even farther away from the decision boundary, from being on the correct side, and also from being on the correct side of the margin as well. We can also have another kind of case where maybe I have a data point that is correctly classified, okay? So technically it's actually on the right side of the decision boundary, but you can see it's still violating the margin, right? The margin is supposed to be the minimum distance to any data point, but we can clearly see that this data point is closer to the decision boundary than these other data points that define the margin. This is also allowed in the soft margin SVM, where we're basically saying, well, I would really like for my margin to be this big, right? Because we're trying to maximize the margin. But here, this data point is making it such that I would need to have a smaller margin, right? Like my margin would be much smaller if I use that data point as a hard constraint. And so instead, it's going to make sense for me, even though I'm still correctly classifying it, it's going to make sense for me to incur some slack there, right, in order to be able to maximize my margin by sort of disregarding it as one of the points that defines my margin. So here, we're also going to have some slack, okay? And there's a little bit of a difference between these two cases, between the cases where a data point violates the margin but is still on the correct side of the decision boundary versus data points that are just completely on the wrong side of the decision boundary to begin with. So for these data points that violate the margin, okay, but are on the right side of the decision boundary, we're going to have xi i's, like I said, it's hard to write, that are less than 1, okay? Why is that? Well, if xi I is less than 1, right, then my constraint still looks something like yi times W transpose Xi plus B is greater than or equal to 0, right, which means that it's still correctly classified. It's just within the margin, right? So I wanted the margin to be defined as 1. This is going to be some number that's smaller than 1, but it's still, greater than 0. It's still correctly classified, okay? Xi I less than 1, but, greater than 0. Right, that's the other part. For these points, where for these other 2 points where these points are straight up incorrectly classified, right? Then I'm going to have xi I greater than 1, which basically says that actually now my classifier is actually producing the wrong prediction for this data point, right? Maybe this data point is like a negative, so yi is -1. But then the sign of my classifier is positive. so I predicted the positive class. So I'm getting it wrong, therefore that constraint is now completely violated, and it's not even going to be greater than or equal to 0, right? It's just going to be less than 0. And so these are kind of the two different cases that we can think about where we might incur some amount of slack, okay? Maybe it's still correctly classified, but it's on the wrong side of the margin, or maybe it's just completely incorrectly classified to begin with. Yes? So is the setup basically going to be the same between the hard and the soft margin SVM? Basically, yeah, that's going to be the case. We're just going to be introducing these slack variables, and we'll show on the next slide how these actually come in. But it'll look very similar to what we had before. Great, so let's talk about that. Okay, so we've introduced these slack variables, right, which basically say, you know, some of my data points are allowed to be on the wrong side of the decision boundary, or at least on the wrong side of the margin, right? And this is great. We've set up the mechanism for allowing for incorrectly classified data points, which we might need if the data are not linearly separable, right? But of course, we still want to minimize how many data points actually do this kind of violation, right? We don't want to just say, well, any data point can do that, because then we're not going to learn anything useful, right? So somehow now we kind of have these competing objectives. We want to be able to maximize our margin for whatever data points we are correctly classifying, but we do still want to maximize the number of data points that we correctly classify in the first place. And so when we have this kind of situation, it's basically like we have two objectives that might be at odds with each other. So what we're going to do is we're going to have both of them as part of our objective, and then just have some coefficient in the middle of them that tells me how much I care about this one versus how much I care about that one. So the optimization objective that we're going to get is something that looks like the following. Okay, so ignore this part for now. Okay, this part is exactly what we had before 2 slides ago. This is just our new set of constraints. Let's focus here. Okay, so this is what I had before. This is saying maximize the margin, right? That's the hard margin SVM that we had. We're basically just adding another term, right, to our optimization problem that says minimize the total amount of slack that I am incurring, okay? So just the sum of all the slack variables, which remember are all non-negative, right? Just minimize that total amount of slack that I'm incurring. And you can see here that, you know, over here I have added all of the slack variables xi, right? So I'm using this bold xi to denote the vector, right? The n-dimensional vector of xi's. Minimize with respect to that as well, right? So minimize with respect to the xi's how much the total xi's actually incur me, okay? And then this is where our c comes in. This is our coefficient, which we choose, which tells us how much do we care about correctly classifying all data points, right? Which would be the sum of all my xi's, versus how much do I care about building a classifier that has as big of a margin as possible, okay, on all of the remaining data points that I am correctly classifying. That would be this term right here that we had before in our hard margin SVM, okay? So this is our new optimization problem. We just added this notion of slack variables. We say we want to allow for data points to be on the wrong side of the margin or the decision boundary, right? And that's controlled by each individual slack variable xi for that data point xi, yi. And then what we do is we say that we want to minimize how many of those we actually incur, subject to, this c, which controls how much we care about that versus how much we care about our original objective in the first place. So as it turns out, this is actually still a quadratic program. The objective is quadratic and the constraints are linear. So there actually are still very good algorithms for solving this. Any algorithm that we could have thrown at the hard margin SVM basically is going to be equally good for the soft margin SVM, right? So we have the same tools that we have. I didn't tell you what the tools actually are because it's kind of out of scope for this class, right? But we had those tools that were good for the hard margin SVM, going to be equally good for the soft margin SVM. So this is good. This is still a problem that we can solve. And like I said before, C, or sometimes people call it lambda, right? But we're going to call it C. C is a hyperparameter, which means that we have to set it ourselves, okay? And we can sort of think about intuitively what it means to set this hyperparameter C, okay? So what does it mean intuitively if my C is really large, 1,000, 1,000,000, whatever? What does that intuitively mean? Yes? Exactly. So as my C gets larger and larger, we're doing more penalization, right, of data points that are violating my previously hard constraint, right? So as my C grows and grows, we expect to see fewer and fewer data points that are going to be on the wrong side of my decision boundary, on the wrong side of my margin, right? What happens as I shrink C to 0? This is a bit of a trickier question, actually, because it's not quite as intuitive. But you know, if you answer with the relatively simple intuitive answer, that's also a good start. Yeah.
Well, I want to say that it just becomes our previous decision boundary model, but I don't think I can say that because of such that condition.
Yeah, so actually this is a great place to start from. So it kind of looks like as C goes to 0, right, then we just have this hard margin SVM that we were working with before, right, which was like minimize, you know, minimize the norm of my W, which corresponds to maximizing the margin subject to the correct constraints, right? But that's the key point, right? The constraints in the hard margin SVM were crucial for actually tying the whole optimization problem together, right? It only made sense to minimize the norm because we had these constraints that all of our data points had to be at least, you know, 1 away from that decision boundary that we had, right? So now, if we have these additional xis and we say minimize this, well, our constraints are no longer correct, right? We're basically saying, well, actually, we had this before in the hard margin SVM, but now we have this additional xi that's basically saying, well, actually, you can predict whatever you want for every single data point. I'll just set the xi accordingly, right, such that, you know, we don't actually, you know, violate this constraint, and then we don't even care, right, about what the xis are doing, right? So then if C goes to 0, we start to get, you know, these pretty weird degenerate problems where, you know, the decision boundary might not lie anywhere good in our space because all we're doing is basically minimizing the norm of our W vector, right? We're minimizing that while not really caring about whether our data points are even correctly classified in the first place. So it gets pretty weird when C gets too small. Okay, when C gets too small, it almost looks like we recover the hard margin, but we don't, right? Because we have this additional degree of freedom that's kind of messing everything up. But as C grows larger and larger, we do get this scenario where we kind of move back towards something that is really trying to correctly classify as many data points as possible. And you might actually think of that intuitively as something like moving towards the hard margin SVM, right? Because we're moving towards a decision boundary that's trying to get as many data points correct as it possibly can. Question? How do we determine the xi values? Yeah, so the xi values are actually part of the minimization itself. So in the machine learning context, we can think that we're actually learning these xi's, right? We're optimizing them jointly with this W and this B that we're learning. That's a good segue, though, into thinking about, well, what if my C was not a hyperparameter? What if it was just a parameter? Okay, what if I actually just learned C alongside everything else? What if I added C to this minimization that I'm doing? Okay, what would happen in that case? Yes? Yeah, so C would just become 0, right? Because the way to minimize this thing is to set C to be as small as possible. Okay, let's say that we constrain C to be non-negative, right? Otherwise it would go to negative infinity. But if we constrain C to be non-negative, then C is going to be just going to 0, because that's the way that it can minimize this objective from its perspective, right? So that's no good either, right? As C goes to 0, we get these really weird degenerate problems, right? And we get these solutions that really don't quite make sense to us. And so we want to make sure that we set C ourselves in order to try to learn a good classifier from our perspective, right? Something that isn't going to, just like, satisfy, this objective, but actually we think will, generalize well to any new data that we might want to do prediction on. Okay, so we already answered that question. How does varying C change the decision boundary that we learn? Make sure that, you can sort of answer that for yourself. Yes? It's called Xi. So I think I missed the first part of the question. Like, are you asking about whether, like, how it's set? Yeah. So it's learned, right? Oh, how is it learned? Well, so the learning occurs jointly with learning my actual decision boundary, W and B, right? So the details are a little bit gory, right? Because basically, I think it's not very instructive to go into the math of how like these QPs are actually solved, but you can sort of intuitively think about it as like, W and B and Xi, they're all like, working together to try to figure out like, well, okay, if W gets set this way, or if W and B gets set this way, such that I have this decision boundary, right, what does Xi have to be in order to make sure that all the constraints are satisfied? And then you can like measure the objective, see whether or not that's good, and then you can sort of try to tweak, like, oh, maybe if I tweak my decision boundary in this way, then I can reduce the amount of slack, the amount of Xi I that I need in total, and then maybe that makes the objective value better, depending on whatever C is, right? So it's a fairly complicated optimization procedure, but the high-level idea is that the Xis are being jointly optimized with the decision boundary that we're actually learning. That's exactly correct. So Xi is a parameter, just like W and B are parameters. Xi is specifically an n-dimensional vector, right? Because there's one for every single data point from 1 to n, right? And then we're finding the optimal setting of that vector. Yeah. Hmm? Let's take a little quiz. Okay, so here's an image that I found from, well, it's from this URL originally, but I actually found it from Professor Jennifer Lisgarten's slides from last semester. So here we have this depiction of, well, I have, every single data set is the same across all these pictures, right? And I have two classes, this yellow class and this purple class, okay? And we can see that it's not perfectly linearly separable. There's some, weird mixing going on in the middle here, where some of the purple and yellow kind of overlap, right? And so we're gonna use a soft margin SVM in order to try to solve this problem. And then the question is, let's say that I tried a few different values of C. Okay, so I tried C 0.1, 0.15, 1, and 100. Okay, and then I got 4 different solutions, 4 different decision boundaries out of these different settings of C. So then the question is, match the correct value of C to the decision boundary that it corresponds to. Okay, so take a moment to look at this. Can anyone give me one match that they think should fit? Yes. Kind of hard to see the pink dots. Yeah. Do I have light control here? How's that? Better? Okay, we'll just do this for now. Actually, I kind of like this better. Maybe I'll just keep it like this. Yes? Okay, so we think 0.1 for this bottom right one over here. Okay, why? That is exactly the right intuition, right? So as my C shrinks, remember, right, we're penalizing the slack less and less, right? So we're basically saying, even if I get a lot of data points classified incorrectly, I'm still not going to be, incurring that much additional loss, right, in terms of my objective. So if I set my C way too small, then it oftentimes can be the case, it depends on the problem, right, but it oftentimes can be the case that with a too small of a C, I'm going to get a lot of data points that lie on the wrong side of my decision boundary, okay? And why is it doing that? It's doing that because basically the only part of the objective that it ends up caring about is minimizing the norm of W, and there's no great intuition for what exactly that's going to look like. It kind of depends on your problem. But as it turns out, for this particular problem, this corresponds to a W that has smaller norm. And so this is the decision boundary that it's going to find because it doesn't really care about getting the data points correct. Yeah, absolutely. How about we skip to 100, C equals 100, and then someone can tell me what they think that corresponds to. Right, so interesting. So actually, one of these should be 100, right? I actually forget. One of these should be 100 because it has the fewest misclassified data points, right? Misclassified is a good proxy for sort of eyeballing these things, but we should remember that mathematically, it's also not just misclassified. It could be correctly classified but lies within the margin, right? That's another way that we can incur slack, right? So I don't remember which one of these actually is, but maybe I have a clearer picture here. So I think that it's probably actually this one that misclassifies fewer data points. But yes, the intuition is correct that these top ones should correspond to larger values of C, where basically it's saying, well, actually now we care about how much slack we incur. And so, because of that, we're going to want to, make sure that more data points are classified correctly or, lie on the correct side of the margin so that I can set those at I is equal to 0. So here are the answers. So yeah, so we have, 101 up 100, C equals 100 and C equals 1 actually look quite similar, which basically means that at least for this problem, it kind of seems like big values of C are starting to saturate, right? Like even if I increase much more beyond 1, I'm not going to get that much different of an answer because 1 is already big enough. Whereas down here, we see more incorrectly classified data points because our C is set too small. And it kind of seems like 0.15 might be a little bit of a critical point because as we move lower than 0.15, then we start to get these really degenerate solutions. But that's going to depend on the problem, right? Yes? Right, so basically what we're saying, right, is that if C is set very low, all it cares about is minimizing the norm of W, right? Because it's like norm of W, or 1/2 norm W squared, right, plus C, some small number, times the sum of all the slacks. So if C is really small, just disregard the second part, and then all we care about is minimizing 1/2 norm squared of W, which, like we said before for the hard margin SVM, actually used to correspond to maximizing the margin, but here it doesn't anymore because we changed our constraints, right? Our constraints now have these i's, which kind of screws everything up. Yeah. How do we visualize the support vectors? That's a great question. I think I have one slide at the end for that. Sorry, I lied. I don't. I have one slide at the end of next lecture for that. But basically, the support vectors are going to be anything that either lies on the margin or in the margin or on the wrong side of the boundary. Those are going to be all of our support vectors. And we'll get into a little bit more detail about that next time as well. The point where there's no more wrong colors. You mean like the point past? Oh, that's interesting. So I believe, okay, so basically what we're saying is I don't know if it's going to be particularly legible if I draw on this, but I'll try anyway. Oops. So, for example, for this one right here, right, the margin, I'll draw it in green, does not actually necessarily correspond to this closest point here. So we're saying that the margin might be like this one because this one is it's past the last pink one. Not necessarily, because the pink points, remember, if they're incurring slack, they could lie within the margin or they could lie past it, right? So the margin could be smaller than the last pink point. And in general, I think that if we don't have the margin already visualized, like we don't actually, if we don't at least know what the W is, then we're not going to be able to sort of deduce it just from the data points. That's my intuition. Yeah. Yes?
So did we say at what point like we would think too high of a C would then not be this generalizable?
That's a good question. So I think the very general theme of that question is how do we even pick C in the first place? Like, we could keep cranking it up and maybe we have less incorrectly classified data points, but is that necessarily good? Not necessarily if we have like outliers or different things like that, which might mean that we would actually want to try to ignore those, right, using some smaller value of C. So the general way that we try to set C or any hyperparameter in general is through a process which we call validation, where we sort of hold out some data that we're then going to try to use to figure out what the best C is. But we haven't actually gotten there in this class yet. We're not going to talk about that for another, I think, 2 weeks. Yeah. But remember all your hyperparameters that we've seen so far. Okay, we've seen like lambda and like L2 regularization and L1, and now we have C and learning rate, things like that. Hold on to all of those because in about 2 weeks we're actually going to talk about what it is that we do in order to set those values. Okay, because we're not learning them, we're setting them ourselves. We're going to talk about how to actually do that. Yes. How do we distinguish between a C100 and a C1 case? I didn't, right? I just kind of took a random guess by thinking about like which one kind of looks to me like it's incurring more slack, and I think that maybe I have a clearer picture on my tablet than is actually projected. So I think I saw like slightly more incorrectly classified points in the top right than the top left, but I kind of just flipped a coin. Yeah, so there's not a great procedure for that. Yes?
Does it have anything to do with the norm of W? Because like if we increase C to 100, can like care less about like the norm of W so that like the slope of the hyperplane will change?
Yeah, that's a great question. So as we increase C from 1 to 100, we could also be, at the same time affecting what W we learn, right? Because we have, essentially we care less about big norm W's as we crank C up, right? So W could learn some larger norm thing that maybe classifies the data points a little bit more accurately, right? And that would change, in general, it could change like the slope and also the bias and things like that for what gets learned there. However, that is not how I distinguish between these two, because I actually, I don't know intuitively what norms these W's would correspond to. Yeah. Another question over there? Okay. Cool. Okay, let's do a little bit of math, actually. So we have this current formulation of the soft margin SVM. It looks kind of nice. Like I said, it's a quadratic program, so there are good ways for solving this. But actually, we can actually make this a little bit simpler. There is no particular simplification to the hard margin SVM that makes it easier to work with. But actually, what's kind of cool about the soft margin SVM, or another cool thing about it, is that because we've introduced these xis, I can actually rewrite this problem in particular as an unconstrained problem. Okay, argmin of something without any constraints whatsoever. Okay, and here's how we do that. The first thing I'm going to do is I'm going to rewrite my constraints. So I will keep this one. This one will stay the same. What I'm going to do for the other constraint is I'm going to move xi I to be on its own side. Okay? So I'm going to say xi I greater than or equal to 1 minus yi w transpose xi plus b. How did I get that? I just basically swapped the xi I and the term on the left, right? So same constraint that we had before, just algebraically manipulated into something different. However, now I have two constraints that say xi I greater than something, right? So xi I is greater than or equal to this, and xi is also greater than or equal to 0, right? Both of those things are true. What does that mean? It means that I can actually rewrite two constraints into a single constraint. Oh god, that one's bad. Xi greater than or equal to the maximum between these two things. 0 and 1 minus yi w transpose xi plus b. Okay, this single constraint is the same thing as the two constraints that we had before. Okay, because xi has to be greater than both of these things. A small note: why did we write it as two constraints before? We wrote it as two constraints before because those two constraints are both linear constraints. Okay, which made it a little bit easier for my QP solver to actually give me an answer, or not a little bit easier. It made it feasible to use quadratic programming techniques in order to solve this problem, right? I have transformed two linear constraints into one nonlinear constraint because max is nonlinear, right? So just because I reduce the number of constraints doesn't actually mean I made the problem easier to solve. It just looks a little bit nicer and it makes it a little bit easier to do the following math that we're gonna finish with. Okay, so we have now that xi is greater than or equal to the max between these two terms. Okay, however, we are minimizing xi, right? This xi is part of my minimization. So if I say that xi has to be greater than or equal to this value, but I'm minimizing it, then what value is it going to take? That thing, right? Because it's not going to be larger than the minimum that it has to be if we're minimizing it, right? But it does have to be larger than this thing that is specified by the constraint. Therefore, that one was really bad. So therefore, this xi is going to be equal to the max that I wrote above. This annotated version of my slides that I'm going to put up later, it took like 1.5 times longer than usual because I was making all the xi's really pretty. And it's just, I think it's very difficult. This is true for all I, right? All of my xi's are going to be equal to the max between these two things, 0, or how wrong I was about data point I. That's basically what this is saying, right? So now, actually, I have figured out what this xi needs to be in my minimization problem. I've figured out the xi that will minimize this thing, right, with respect to xi, that simultaneously satisfies these constraints over here. That means that I can get rid of these constraints because I know that this satisfies those constraints, right? And I can just substitute this value this expression directly into my optimization problem objective, okay? So my new unconstrained optimization problem is going to be a minimization over just W and B, right? Because we know what the xi's need to be, so we're no longer minimizing those. We have expressions for those, right? Of basically the objective that we had before, but with this value of xi that I have found. Okay, so swap xi with this expression, max of 0, 1 minus yi w transpose xi plus b. And then this thing becomes my new unconstrained optimization problem, which is the same as the original soft margin SVM constrained optimization problem that we have at the top of this slide. And this is kind of neat because it's nice to not have constraints, actually. It makes optimization a lot easier sometimes to not have to worry about, well, I found a good value of W and B, but does it satisfy these constraints that I have? Sometimes doing that is just a hassle. And having an unconstrained problem can make things a lot easier sometimes. let's actually take a little bit of a closer look as to what it is that we found here. So if you didn't finish writing it down, it's here as well. I moved some terms around, but that's okay, right? It's still the same thing that we had. This is the new unconstrained version of the optimization for the soft margin SVM. This version is basically a loss function, right? So we're trying to minimize this loss function, right? It defines a loss function that has two components, right? The first component is what we call a hinge loss, okay? It's called a hinge loss because it kind of looks like a door hinge if you visualize it. But basically, what it's doing is it's trying to encourage, it's a particular loss that tries to encourage accurate classification, right? It's basically saying if my classification is incorrect, right, and also incorrect with respect to some margin, right, then I'm going to incur some particular loss here, right? But if my classification is correct by the necessary margin of 1, then this whole term is going to be negative, and then so I'm going to incur no loss because it's going to be 0 for that particular data point. And then I sum that hinge loss across all of my data points to get my total loss on the data set, right? So this hinge loss is encouraging accurate classification. We saw different types of things like this before. We saw like, negative log likelihood loss and mean squared loss and all these different types of things. Hinge loss is just another type of loss function that I could define. And as it turns out, it's kind of the one that SVMs end up using, right? We have this hinge loss, and then we have another component, which is actually just L2 regularization, right? It's just, norm squared, two norms squared of W. That's basically the L2 regularization term that we had before, right? So this is actually kind of neat because we have a particular view of SVMs that we've derived, right, where basically this term is trying to maximize the margin, right? But there's another interpretation of SVMs, which basically is just L2 regularized hinge loss minimization. These two things end up being equivalent, but it's kind of neat that SVMs can be understood from both of these different directions, okay? And one of them being just classic L2 regularization that we've already seen for different topics in this class. One last thing that's quite nice, I said before, right, that constrained optimization problems, sometimes they can be solved, like quadratic programs can be solved, and there are pretty good solvers for it. But it is quite nice to move from that to an unconstrained problem where you don't have to worry about the constraints being satisfied, and there's a much wider set of methods like iterative optimization, like gradient-based optimization, right, that we can use in order to try to solve these problems, right? And so modern methods for solving soft margin SVM problems actually usually use this form of the optimization, the unconstrained version, and then use methods basically that resemble what we've talked about before, like these gradient descent kind of methods or stochastic gradients, things like that. So they're not exactly the same because they use technically what are called like subgradient methods for not purely differentiable functions, but the ideas are extremely similar to what we've already seen when we talked about gradient descent. And that's basically how people usually solve SVM problems these days, is with these gradient type methods. On the unconstrained optimization problem, which is great because we couldn't do that for the constrained problem. Okay, we're going to end on time today because I just have a summary slide. So we modified our SVM formulation, right, to include slack variables, which allowed us to handle non-linearly separable data because the slack variables say these data points can lie on the wrong side of the margin or even on the wrong side of the decision boundary if we really needed to. And we introduced an additional hyperparameter C, which allows us to control for how heavily the slack is penalized, right, which would be for larger C's, compared to maximizing the margin. We just saw how we can reinterpret this constrained optimization problem as an unconstrained problem that combines these two terms, a hinge loss with L2 regularization. Right? And modern methods, you can think of them as basically solving this problem with gradient descent, which is kind of nice. On Friday, we're going to talk more about SVMs, and we're going to get even more confusing, okay, because we're going to talk about primal dual formulations of SVMs, and that's going to lead us into next week as well. If you have time before Friday, it would be quite useful to review the method of Lagrange multipliers and just be a little bit familiar with what that is. But that is optional. You might just have an easier time following along on Friday. Okay, so that's all for today. Thanks.